morning, everyone. It's a very early morning for everyone, I think, because it's raining. So not many people yet, but I'm sure they will be joining later. So today we are very honored to have our two speakers from Seoul National University, Professor Park Chung-kyu and also Dr. Kim Hyun-ji. So I'm sorry to apologize that actually they have to catch a flight to Bangkok at 8:45. So we'll end this session early. So each of them will speak for 20 minutes and then we will do a short Q&A together. So without further ado, I will first introduce Professor Park. So both of them, Professor Park and also Professor Dr. Kim, they are both from Department of Microbiology and Immunology, Seoul National University, College of Medicine. And interestingly, both of them are actually clinician scientists. So it will be interesting for all of us to actually know what it takes for medical doctors to become a scientist. And interestingly, Professor Park also have a company. So I think with his presentation, he'll tell us more about his product and its breakthrough. So without further ado, I will pass the time to Professor Park.
Okay, good morning, everyone. Thank you for kind introduction, Professor Chan. I'm very glad to here in this webinar. I'd like to start my talk by sharing my slides. Okay. So let me start my talk. I will talk on the regulatory T-cell therapy for control the autoimmune disease and prevention of transplantation rejection. This slide shows the list of my talk, the contents of my talk. There are many kinds of Tregs, but I'd like to focus on CD4 positive Tregs today. The Tregs, CD4 positive Tregs is generated from either thymus during the education of T cells. So the T cells which recognize self-antigen stronger than the effector T cells will have FOXP3 transcription factor and CD25 surface antigen, and they migrate out from the thymus. They exert the suppression function to inhibit the T cell responses, not only effector T cells, but also other immune cells, including B cells, NK cells, and macrophages. The other CD4 positive Tregs come from the secondary lymphoid organ. So they recognize antigen in the presence of IL-10 or TGF-beta. They became regulatory T cells. So they are called as inducible Treg, and in other words, peripheral Treg. And they also express FOXP3 and exert the same function as those come from the thymus. How these Tregs come in the world, I'd like to talk about the black history of suppressor T cells. So the concept that some lymphocyte could control the responses of other lymphocyte was proposed many years ago in 1971, and was soon followed by experimental demonstration of populations of T lymphocytes that suppressed immune responses. So these initial findings led to enormous interest in suppressor T cells, which became one of the dominant topics of immunology research in the 1980s. However, this field has had a somewhat checkered, turbulent history, mainly because attempts to define the populations of suppressor cells and their mechanism of action was largely unsuccessful. So in the 1990s, the idea had an impressive rebirth with an application of better approaches to define, purify, and analyze populations of T cells that in immune responses. So these cells are called regulatory T cells to differentiate the suppressor T cells that would not be defined at that time. One big figure who contributed to discovery of regulatory T cells is Dr. Shimon Sakaguchi. In 1995, in his seminar paper, he showed that one cell population, CD4 positive T cells expressing a high level of IL-2 receptor alpha, in other words, the CD25, is the it plays a critical role in maintaining the self-tolerance. So it takes actually more than 5 years to define these regulatory T cells. He started from CD5 positive T cells, but as you can see here, the population ratio is too high to be defined as some T cells which could control as suppressor T cells. So finally, he find a T cells, CD4 positive T cells with a 5 or 10% of peripheral CD4 positive T cells play a critical role. And then he also find that the master regulatory transcription factor of FOXP3. So when there's some mutations in FOXP3, then either the mice or human became immune deficient, and they have a lot of autoimmune disease and inflammatory bowel disease. So in human, this disease called IPEX, immune dysregulation, polyendocrinopathy, enteropathy, X-linked syndrome. And we could find the same disease model in mouse. It is called as scurvy. So now the regulatory CD4 positive regulatory T cells is defined as CD4 positive, FOXP3 positive, CD25 high, CTLA4 positive, and CD127 low. The function of Tregs would be classified as 4, as shown in here. The one function is by releasing inhibitory cytokines such as TGF-beta, IL-35, and IL-10. And the other is cytolysis by releasing granzyme A or granzyme B with a perforin, so it can induce the apoptosis of effector T cells. And also it expresses a high level of CD25, and it can bind to IL-2 and mapping of the IL-2 so that the effector T cells could not have these growth factors, so they will be induced to be apoptotic cell death. And also the regulatory T cell express CD39 and CD73, which converts the ATP to adenosine. And by binding to adenosine receptor, the effector T cells became inactive. So lastly, the expression of CTLA4 bound to CD80 and 86, so that the antigen presenting cells could not provide this co-stimulatory molecule to effector T cells, as the binding affinity of CTLA4 against CD28 is 100 times higher than the CD28 in effector T cells. And also they induce the trogocytosis, so they deplete the CD80 and 86 on the surface of antigen presenting cells. And also LAG3 inhibit the dematuration and function. So these Tregs is very important in controlling autoimmune disease, have been shown by Dr. Jeffrey Bluestone in autoimmune diabetic NOD mice. As you can see here, if the mice deficient CD28, as Tregs are dependent on CD28 signal, the mice doesn't have any regulatory T cells enough for controlling the autoreactive T cells. So they got diabetic in early time point. But if you adaptive transfer the regulatory T cells, you can suppress and control the autoimmune type 1 diabetes. Also, he showed that the regulatory T cells exert their suppressive function from the stage of antigen presentation for the initiation of activation of effector T cells, and also they exert their function on the effector site in type 1 diabetes, in pancreatic islets, for protecting the beta cells from destruction. And he also nicely showed that the regulatory T cell number conversely related to the interferon gamma positive Th1 cells. So in this disease model, he actually executed a phase 1 clinical trial for the treatment type 1 diabetes by using ex vivo expanded polyclonal regulatory T cells. Now he is preparing a phase 2 study in autoimmune type 1 diabetes. The regulatory T cells also could control the rejection of transplantation. It has been shown in many papers that these Tregs are important in prolonging the graft survival. And we also showed in islet transplantation model that the donor-specific regulatory T cells mediated the immune tolerance. So in this model, we made a black B6 mice diabetic by injection of STG and treated with the anti-CD154 antibody, which could block the CD40 ligand pathway and transplant them with a allogeneic Bell-C islets. As you can see here, the single treatment of anti-CD154 prolonged the graft survival indefinitely. And so when we deplete the regulatory T cells in direct mice, where the regulatory T cell express the receptor for diphtheria toxin. So if you inject the diphtheria toxin to these mice, the Tregs depleted and the graft got rejected. So this shows that the regulatory T cells is critical for maintaining the immune tolerance against allogeneic pancreatic islets. We also showed in xenotransplantation model where the porcine islets were transplanted into diabetic mice with the single treatment of anti-CD154. We could prolong the graft survival indefinitely. And you can see here the insulin secreting pancreatic islets sitting underneath the surface of underneath the kidney capsule. If you deplete the regulatory T cells by using anti-CD25 antibody, the graft got rejected in early time point. And you can see the depletion of regulatory T cells from the peripheral blood. And also, if you adaptive transfer, if you treat the mice in early time point with a neutralizing TGF-beta, you can also induce the graft rejection, indicating that these regulatory T cells was induced from the environment which has high level of TGF-beta. So this is kind of inducible Tregs. And adaptive transfer of these Tregs could prolong the graft survival, and these Tregs infiltrated into the graft. We also showed this effect in non-human primate model, where we isolated the islets from the designated pathogen-free pigs. So as you can see here, the DPF pig, very clean pig, it can be used as a source of xenotransplantation, organ transplantation in human. So we procure the pancreas, and islets were isolated under GMP facility. As you can see here, you could find the islets isolated. And we transplanted the islets into the monkey through the jejunal vein into the liver. As you can see here, the islets are infused through the jejunal vein into the liver. And then these monkeys were treated with immunosuppressive regimen. And on top of that, we infused the regulatory T cells between 0 to 16 days after transplantation. The regular T cells was isolated from the peripheral blood and were expanded ex vivo through 3 times of stimulation during 21 days. And the Tregs were expanded 2,000 to 3,000 times. And after confirming the FOXP3 expression and their suppressive function, we infused these Tregs into the recipient monkey. And if we label the Tregs with the CFSE, we could observe the Tregs circulating from the peripheral blood by the time 97 days post-transplantation. This slide shows the graft survival and controlling the blood glycemic level. As you can see here, the green green line indicate the fasting blood glucose level, and the pink bar indicate the exogenous porcine insulin. So as you can see here, 4 out of 5 monkeys maintain normal glycemia for over 6 months. The longest is about 2 years. So very interestingly, in Treg infused group, they showed that high level of CD8 positive, CD28 negative T cells. And also the glycemic control inversely associated with the level of CD8 and CD20, CD8 positive, CD28 negative T cells, indicating that these CD8 positive, CD28 negative T cells suppress the immune response. So if you adaptive transfer the Tregs, you can control the allo-reactive T cells so that you can induce the immune tolerance against allogenic antigen. So there are 4 ways for apply these Tregs as therapeutics. The one is in vivo expansion of natural Tregs by injecting low-dose IL-2 or rapamycin. And the other way is in vitro conversion of conventional T cells by stimulating them with antigen in the presence of, as I told you before, IL-10 and TGF-beta. And the third way mostly applied is ex vivo expanded Tregs, as shown in non-human primate model. And lastly, the in vivo conversion of conventional T cells into the Tregs. And yeah, it's in challenging. But still, we have some limitations for Treg therapy because they have very low number and they show the instability in functionality and also in plasticity. And if you use the polyclonal T cells, you're having difficulties for targeting the specificity. And we also have the allogenic reaction. So to overcome this, in PB immune therapeutics, we found a way to expand high number of antigen specific polyclonal Tregs, and this is PB201. So we could expand them to 5,000 to 8,000 times. And the other way is to make CAR Tregs, which could be induced in the inflammatory environment to be regulatory T cells. This is our innovative strategy where we could put the CAR on the surface and put the signal domain inside. so that the T cells which recognize the inflammatory condition antigen, then it could become a regulatory T cells. And our final goal is to have a universal donor with this a platform, so that we could apply these therapeutics out of vial. Yeah, I'd like to wrap up my talk here, and thank you for your attention.
Thank you, Professor Park. So I'm sure we actually know a lot now about Treg and also its roles in autoimmune disease and transplantation.
Yeah.
We'll answer the questions later. We will move on to Dr. Kim Hoonji.
Okay.
Thank you, Professor Park.
Thank you.
Yeah.